Let's take a look at something called allosteric enzyme inhibition, or allosteric. But I'm going to start with a silly analogy here. I'm going to pretend like we're in an M&M factory here, and these are the various workers, and they work in a chain basically. So the chocolate bar has to be shaped into little ovals. The ovals have to have a nut added inside, and then this guy is going to put a candy shell on the outside, and then this one does all the stacking, piling up, or something like that. So this is an example of a chain, a production chain, and each one of these guys represents one particular tool in the process here. Now, in the production of M&Ms, let's say everything's going really well, and we're getting like tons of these M&Ms here. Let me add a few more, and we've gotten to the point where there's just too many M&Ms piling up. We can't ship them off fast enough. People are not buying M&Ms as fast as we want them to, and we just have a ridiculous number of M&Ms. So we have to stop the whole thing. So the stupid example here is that in the end, these M&Ms pile up so much. Where's my infinite one? I can't find it anymore. Anyways, these M&Ms pile up so much that somebody in the end here just starts chucking them back, saying there's too many, and he throws them back like a football, these giant M&Ms, and it knocks out this dude right here. Alright? And he's got a pile of M&Ms around him. And if that guy gets knocked out, then he can't actually shape these into ovals. He gets left with nothing to do. And the whole thing shuts down. But that's a good thing, because we have too many of these M&Ms. And then as these get shipped off, as these things get shipped off, and we have less and less of them, then eventually we have to shift these ones off as well too. Or maybe he doesn't get knocked out, he just eats too many and falls asleep, or something like that. But eventually those get shipped off as well, and then there's nothing kind of stopping him anymore, because there's no more constant bombardment of M&Ms trying to knock him out, and he comes back, and it makes sense now, because now he can shape these chocolate bars into ovals, add some nuts, add the candy shell, and then we start producing more and more of these as we're supposed to have. So that's a good thing. What have I just done here? I'm using this as an analogy to show you that these could be enzymes in a pathway. This is the initial substrate that gets worked on by this enzyme, gets turned into this thing gets worked on by this enzyme, and then so on and so forth, and we end up with a final product here. And the final product, if there's too much of it, the final product can come back and inhibit this first enzyme. And if it inhibits this first enzyme, then the whole production line shuts down. And it works as a kind of negative feedback mechanism. When there's too much of the product itself can actually inhibit this enzyme and slow down everything, when we don't need too much of this. And then when there's not enough of the product, well, this stops inhibiting this first enzyme, and everything can go back to working normally. So we only have to mess with this first guy, mess with this first actual enzyme here. So in reality, many metabolic pathways can be chains, they can be cycles like glycolysis or the Krebs cycle. This is normal in biology, and each of these steps in the chain is worked on by one enzyme, starting with one substrate, which turns it into a product, and the product becomes a substrate of the next reaction, blah blah blah, until you end up with the end product. And this end product can be very useful sometimes. So let's go look at this in more detail here. So here we're going to take a look. Here's a particular pathway. This is an enzyme over here, and this is the substrate that's supposed to bind. So binds to this, gets converted to this, to this guy. This guy binds to the next enzyme, gets changed slightly, binds to the next enzyme, gets changed slightly, so on and so forth, till you end up with an end product here. And if there's too much end product, this end product can actually come back and inhibit this first enzyme. So what happens when that first enzyme gets inhibited? Well, let's take a look. This is just like non-competitive inhibition, where there's another site, and we're going to call it the allosteric site. And this end product can actually end up binding to another site called the allosteric site. It causes a conformational change in the actual structure of the enzyme, and then the substrate can no longer bind, and therefore stops the entire pathway. So if this actually comes back and binds here, changes the shape of this particular enzyme, I'm just going to match it over here. Now this substrate can't bind and it ends up stopping the entire thing. So it's just an example of negative feedback. So let's look at some of the words that are important here. It's called allostery. It's an example of negative feedback, and it's end product inhibition. So in metabolic pathways, the product of the last reaction in the pathway can inhibit the enzyme, only the first enzyme, the enzyme that catalyzed the very first reaction. That's all we need to do, actually. And this enzyme that's inhibited is called the allosteric enzyme, because this one kind of controls the fate of the rest of the pathway. So the substrate actually, oh, this is just talking about the beginning. This is what's supposed to happen here. The substrate binds to the active site and it gets converted to the product. And the substrate of the first enzyme is eventually converted to the final product of the pathway, which also acts as an inhibitor to the original enzyme. And here, if the inhibitor is actually bound, well, the substrate is unlikely to be able to bind after the whole shape is actually changed right here. And this end product is also called the allosteric inhibitor. So this is true for a lot of pathways. You don't want to waste a lot of energy in these metabolic pathways making a product unless you need it. So this is a way to make sure that that actually happens. If there's too much of the product, or too much, for example, ATP being produced, then that ATP can actually bind to the first enzyme and halt the production of itself. And then if there's not enough ATP, well, this ATP ends up getting used as well. The enzymes are no longer inhibited, and the pathway can continue again to produce the actual product. So at the end of this entire thing, just make sure you're using the vocabulary correctly. The advantage is that excess buildup of the end product ends up shutting off the entire pathway. So we call this an allosteric enzyme. This is an end product that acts like an inhibitor, so we call it the allosteric inhibitor. Overall, you can say this is called allostery, but it's an example of non-competitive inhibition. It's a specific example of non-competitive inhibition. And I think that's all really that you need to know. Here's a specific example you can pause and take a look at, but that's a lot to stomach. But anyways, pause the video and then take a look at that. That is what we call allosteric enzyme inhibition. Now I'm gonna go get me some M&Ms.